Kahit... Oh! Cool!
This reaction is an example of chemiluminescence. Normally you might expect reactions to release or absorb energy as heat due to different numbers and strengths of bonds being broken in the reactants and made in the products. But every now and again, the conditions are just right to allow for a reaction in which most of the energy is released as light rather than heat energy. We've seen luminol doing its thing back in a previous edition of Exhibition Chemistry in the luminol fountain demonstration. But 2 years ago I saw another luminol demonstration by the YouTube user NerdRage and wanted to share it with the EIC community. In this chemiluminescence reaction, an intermediate is formed in an excited electronic state, like people sledging on a mountain, changing their gravitational potential energy into movement energy. These electrons can relax down to a lower energy level in an atom, releasing a particle of light called a photon as they go. Unlike the sledges though, only certain movements are allowed, leading to very specific frequencies of light being emitted, in our case, blue. Luminol is the molecule that accomplishes this feat. It's perhaps best known for its use in forensics, detecting traces of blood at a crime scene. To get the all-important glow, we need to meet 3 other conditions. We need an oxidizing agent. Hydrogen peroxide is used both in our experiment and at crime scenes, but bleach will accomplish the same end. This can make an investigator's life more challenging if somebody has tried to clean the scene with bleach. Now, the reaction works best in an alkali, and here's why. The first step of the reaction is to remove hydrogen ions. This is what bases were born to do. Another important step involves the reaction of oxygen with the luminol, which kicks off the production of an excited molecule from which we can release a photon of light energy. We need to get lots of oxygen to the luminol quickly if we want that all-important glow. Luckily, that's another speciality of transition metals. They make for great catalysts. Back at the crime scene, transition metal ions in blood spatters do the job for us. Specifically, it's the iron 2 ions which will light up any luminol solution sprayed on them. Our experiment skips over a few elements to copper. Around the copper, a range of complex ions can form. Complex ion formation is another thing transition metals are good for. It sounds complex, but it's not too tough to wrap your mind around. Essentially, the metal ions are surrounded by molecules or ions called ligands, which have lone or non-bonding pairs of electrons. These form coordinate, also known as dative bonds, to the metal ion, and instead of having a simple metal ion, for example, floating around in solution, we have a cluster of particles with the surrounding ligands and metal ion acting as one unit. To some of these complex ions, peroxide can coordinate and react, liberating oxygen and other oxidizing species which can go on to react with the luminol. The key to this process is the capacity of transition metals to exist in a range of oxidation states. Essentially, they're pretty good at shuttling electrons to and from other substances. The YouTube user known as NerdRage had the awesome idea to put a twist on the typical reaction. A coin or piece of copper dunked in the luminol solution will make a glow, but the glow quickly just spreads through the whole solution. If only there was a way of shutting off the glow as soon as it moves away from the metal. Well, this is where the EDTA comes in. EDTA is a polydentate ligand. Polydentate means many-toothed. One molecule can bind to the transition metal ion in more than one place. These polydentate ligands display a property called chelation. Chelation describes the way in which the universe favors the swapping of lots of small ligands for one big one. If the strengths of the bonds are similar, and they tend to be because the atoms involved in the coordination are of the same types, then such a swap means that in the example shown here, we go from having 2 moles of particles floating around in solution to having 7 moles of particles. This is favored by entropy, a way of saying that the universe tends towards a more disordered state. Having 7 moles of particles to play with gives you a lot more room for disorder than just having 2 moles. As we move away from the piece of copper metal, the ions in solution will be gobbled up by the EDTA ligands floating around in the solution we prepared. The hydrogen peroxide just can't get a look in, so the glow dissipates. So, not a great demo for showing the magnetic properties of transition metals, but everything else is covered.